Hello, my name is Sleutel from the Department of Environment, and I'd like to showcase you our collaboration with the core facility for advancing insights into soil functioning. I investigate soils and specifically stability and decomposition of organic matter in soils. Organic matter is a complex mixture of living and dead organic components and stores vast amounts of carbon and nitrogen in our environment. Now, my research is on these carbon and nitrogen cycles, mostly in agroecosystems, and I specifically aim to understand how management and environmental drivers impact these cycles. Now, to understand soil carbon and nitrogen cycles, we need to consider firstly the large scale, where, for instance, groundwater table depth would steer moisture availability, which is crucial for many soil processes. But we also need to know about plant carbon inputs and nutrient extraction. We also must realize that on a smaller scale, it is primarily microorganisms that drive many of these processes by production of extracellular enzymes. Since long, we've wondered why there is so much organic matter in soil and why and how is it being protected against microbial decay. Now, this is relevant to know, for example, when we want to predict greenhouse gas emission from soils. By the study of biomarkers, we in the meantime know that in agricultural soils about half to 70% of organic matter is actually dead microbial biomass or necromass. So to understand the stability of organic matter, we need to understand what leads microbes to either respire or, on the contrary, form biomass, the precursor of much of soil organic matter. For this, we should also like to map the habitat space of microbes, the pore space. Now, even though soil pore space is notoriously difficult to grasp because it cannot be sampled or it cannot be seen, we do realize that that would be relevant to understand soil microbial processes. And together with the UGent Center for X-ray-CT, we have been teaming up for over 15 years to quantify that aspect of soil. Now, to exemplify this, I'd like to introduce you to two parts of our research on organic matter mineralization. The first line at our lab concerns soil moisture availability, which is a key driver of soil microbial activity. We know that there exists a bell-shaped relation between heterotrophic activity and between soil moisture content with optimal conditions at intermediate soil wetness. And we are testing how that mathematical relation is moderated by properties like soil texture or organic matter quality. And we do that to improve ecosystem models. But in our experiments, we also saw several times that, on the contrary to theory, the response of organic matter breakdown to moisture content can be very limited. To understand what is happening, we visualized soil moisture with UGCT's nanowood scanner, and that required contrast enhancement on the soil, liquid phase, and in this case we used also potassium iodine to lift that contrast. In a second step, we also visualized soil moisture content of the organic matter itself in the soil. And we found that in the studied sandy soil that we were looking at, that mineralization was unresponsive to soil moisture because the organic matter itself acted as a sponge. For the studied silt loam soil, such was not the case. Instead, a shift toward a different biomass composition was responsible. But we really needed an eye on the real distribution of moisture in the soil, and we could do that with these CT scans to gain understanding. In another example, we used X-ray CT scanning of the pore space to understand how soil traits co-impact nitrous oxide emissions. Our agricultural lands are net sources of this greenhouse gas, with a typical hectare of land emitting an equivalent of about 1 ton CO2 per year. And in experiments, we also observed that there is a very large impact of soil structure and texture onto nitrous oxide emissions. But we couldn't explain these trends with bulk soil gene abundances, nor with soil pore space traits. But by bulk soil pore measurements, we realized that we actually missed that a process like denitrification actually really occurs in hotspots, so centered around smaller areas in the soil and mostly around organic matter. So we then developed a methodology to visualize added organic matter that we used in our soil cores, and for that we also tested CT contrast enhancing stains like osmium tetroxide, and we also developed a procedure to quantify local pore space surrounding organic matter. And by this we were able to show a good correlation between nitrous oxide emissions, the soil microstructure, by a mutual correlation with organic matter decomposition. We would now like to further develop modeling of gas diffusion as well, using the CT models of pore space that we created with UGCT. And then finally, a third and last example of our research and collaboration with UGCT concerns the usage of CT to visualize plant rooting systems. So root rates are important, for example, for adaptation of plants and vegetation to climate change and in the context of organic matter cycling. With UGCT, we developed a method to visualize maize root systems, and we observed that across 8 varieties, root architecture was much more strongly dependent on the factor soil than on variety of maize, even with optimal nutrient provision. So clearly, researchers working on roots would need to realize that there is a strong interaction with soil traits, and CT could be a helpful tool in this research. In future, we would also like to integrate CT to unravel how roots interact with organic matter and soil structure and test conceptual models. With this, I like to end my talk, and in summary, teaming up with the core facility advanced our research by the excellent versatility of their instruments and software, as it allowed us to work on a very small scale and get insight with good resolution and phase contrast in soils. Also, the ability to have fast access was crucial when working with vulnerable setups like small soil cores. It was always possible as well to run enough replicates to allow sound scientific experiments. And then lastly, I would like to point out the team's helpfulness, especially their willingness to repeatedly test things out before moving on to real experiments. And that was really invaluable, as well as their help with method development. I thank them for the great help over the years, and I also want to thank you for watching this testimony of our fruitful collaboration.